because most of the topics are related to network security. It's not just about enterprise infrastructure. But please do not worry about that too much. We will go through these key points as clear as possible. Should you still have any questions about the contents today, please feel free to contact your tutor. SPOTO has CCIE security course as well. The teacher for the lecture for the security can explain in more details if you need. We will cover the first 3 parts for today and leave the SD-WAN deployment with firewall to the next class. The first one, let's have a look about the certificate, and the key thing we need to talk about to understand is encryption algorithm. What is encryption? Encryption is to encrypt plaintext data into ciphertext data through algorithm to prevent data from being eavesdropped. Mainly there are 2 types of algorithm commonly used on the market. The first one is symmetric algorithm. This means both encryption and decryption use the same key and algorithm for encryption and decryption. Because it uses the same key and algorithm for both encryption and decryption, that's why it's fast and compact. But the problem is, think about you use the same key for encryption and decryption. Imagine you have 10 pairs to do the encrypted communication with you, or 20 or maybe 50. You are not going to use the same key for every single pair, right? Otherwise, everyone knows everyone. So this means you need a pair of key, a same precious key with everyone. If you have 10 pairs, you need 10 keys. If you have 50 pairs, you need 50 keys. That's why the key expansion would be a problem. You need to manage lots of keys, one for each. The other is because we use same key for both encryption and decryption. That's why we need to share the key with each other. So the key transmission is required. And digital signature is not supported for this symmetric algorithm. So these are the advantage and the disadvantage of this algorithm. The other type is a symmetric algorithm. It means we use public key encryption to encrypt. Then we use private key to decrypt. Or the other way around. We can use private key to do the encryption, then use public key to do decryption. Apparently, the advantage is it's a pair of key, right? Public and private, it's a pair. That's why we can share the public key with the other side, and we keep the private key in our own pocket. So the private key does not need to be transmitted. And a symmetric algorithm, it supports digital signature. The disadvantage is obvious as well, because we use a pair of keys, public and private, for encryption and decryption. That's why this algorithm, the computing speed is a little bit slower than the symmetric algorithm. And it's not compact. So as we know, the symmetric and asymmetric algorithm, they both have advantage and disadvantage. Then in the real scenario, as the classic usage, usually we combine the advantage together from these 2 algorithms. How do we do that? As we know, the symmetric encryption is fast and compact. So we use the symmetric encryption algorithm to encrypt the actual data to be transmitted. It's faster. Then we use asymmetric encryption to encrypt the public key, which is used for the symmetric encryption algorithm. It's easy to understand, right? I repeat. So we use symmetric encryption algorithm to encrypt the actual data to be transmitted. Then we encrypt the key of the symmetric encryption algorithm through the asymmetric encryption algorithm, like it shows here. By doing this, we combine the security and efficiency from both algorithms. A typical example of this classic usage is IPsec. IPsec tunnel is a good example. It uses asymmetric encryption to exchange the public key, which is used for encrypt the actual data to be transmitted. However, this classic usage has a disadvantage. It's not able to verify the credibility of the data source. So, in the real scenario, how to resolve that? We have a solution. It's the CA, Certificate Authority. So, Certificate Authority, CA, issues a digital certificate for each user who uses the public key. The role of the digital certificate is to prove that the user listed in the certificate has the public key listed in the certificate. The default CA in Cisco solution is semantic. You can apply a certificate from semantic for your environment. Semantic will validate your identity, then include your validated identity and contact details, and publish it in your digital certificate. The certificate issued by semantic has semantic's digital signature, which prevents attackers from forging and tampering with certificate. Usually the certificate lasts for about a year or 2 years based on your subscription. It is a common practice to use a digital certificate issued by CA in business environment to identify the source. So this is the common practice on the market to identify the source, the data source. This slide explains how the digital certificate works. Let's have a look. We have a user A at the left side and user B at the right side. So first, user A hand over its public key to the CA. In this case, we assume this is semantic. So the user hand over its public key to semantic, and the semantic as the CA, it uses hash algorithm to calculate the public key and get the hash value. In the meanwhile, the user A submit identity information, like the information shows here. It has a CN, means it's China. Province, it's Fujian. City is Fuzhou. Organization, it's SPOTO. OU, SPOTO CCIE. Then semantic will verify this, then use semantic's private key over here. to sign a digital signature for this user A. Then Symantec will put the user's public key and its digital signature, pack them up to be a package. This package becomes a digital certificate. So then the CA issues this certificate to user A. When the user A would like to communicate it to user B, the user A passes its certificate to user B. The certificate, apparently, it contains the public key and the digital signature with information verified by CA. User B extracts the public key from the digital certificate. That's computing for the hash value. In the meanwhile, the user retrieves the public key from CA Symantec. Use this public key to validate the digital signature in the user's digital certificate and decrypt that with the public key. It would get a hash value and compare each other to validate if the certificate is genuine, if the user A is a genuine user. By doing that, the user A passes its public key to user B. In the meanwhile, user B validated this is a validated key from a genuine user A. So this is the process, how the digital certificate works, and how the user A and user B passes the public key from user A to user B. You might be wondering, what if someone in the middle captured user A's digital certificate? Then what will happen? Is the man in the middle able to decrypt the communication between user A and user B? The answer is no, they are not able to. The reason is this is a symmetric encryption algorithm for the communication. So even if the man in the middle patient, that's why even the man in the middle, a man in the middle over here, even captured the certificate of user A, the man still not able to decrypt the communication without the private key. Then you might be wondering, what if someone in the middle create a digital certificate by themselves? Then what happens? The answer is yes, they can. They can create a digital certificate by themselves, but it will not work. Why? Because the digital certificate needs to be verified and digital signed by a CA over here. The second is, even the user at the other end received the certificate created by the man in the middle self. The user B will still go to the root CA to get the public key to decrypt the certificate, to validate the integrity. This process won't pass because the certificate created is not validated and registered by the root CA. That's why use digital certificate is the most secured way as a common practice on the market for nowadays. And as you can see, the most important part, the secret part, most secret part, confidential part, is the private key. The private key in this solution. So you need to protect this well. Otherwise, the communication can be decrypted by the man in the middle. As long as you have the private key not exposed to someone else, the communication is safe. Next, let's have a look about the tunnel between controllers. This is about how the controller and the V-edge communicate to each other. Cisco SD-WAN solution is basically a whitelist model, whitelist architect. It's zero trust model. For the vManage, vBound, vSmart to communicate to each other and being used by the solution, they need to be added into the vManage GUI by the administrator, like this picture shows here. Without being added in this whitelist, it won't work, right? Basically, if it's not in the whitelist, you can't use that, and they don't know each other. Certificate signing through semantic. The solution, the default is use semantic. The process is automatic. But if your environment is not connected to the internet, then you would need to use manual process. Basically, it's download the CSR file. For example, if you have a solution, it's behind the internet, and your environment is behind the internet, then you can download the CSR file. There is a file called CSR file from the vManage. This is vManage box. You download the CSR file, certificate file, then submit this to semantic. Submit this to semantic in the internet. Semantic will verify it with Cisco. Once it's verified, semantic will issue the certificate to you. Then you can import the certificate into vManage by yourself manually. But it is recommended to use automatic model. It's trouble-free, but you just need to expose your environment into the internet. The controller list over here. It's controller list. All controllers registered in vManage are distributed by vManage to all controllers, including vBound, vSmart. Their IP address, serial number, etc. are all synchronized between each other through vManage. So they know each other by once it's in the whitelist. The information will be distributed by vManage to all other controllers. The communication for controllers, list distribution, synchronization are all encrypted. The default encryption method are DTLS, and TLS. Both of them are security protocols that provide security and data integrity for network communications. What are the differences between DTLS and TLS? Actually, more than 70%. More than 70% of them are actually the same. As you can see, DTLS 1.0 is based on TLS 1.1. And DTLS 1.2 is based on TLS 1.2. The essential difference is that DTLS is based on UDP and TLS is based on TCP. So this is the essential difference. More than 70%, they are the same. How does DTLS work? We will briefly go through this. The entire process and the details are quite complicated. As a foundation course of SD-WAN today, we will just cover it at high level. You might need this information for troubleshooting to troubleshoot the related issue during the deployment. We use this diagram as an example. There are two sides. The left side is client. The right side is server. Assuming this is the first communication between this client and server, then the client sends a hello to the server. The server replies the hello verify request to the client, including cookies and session in this request. This is randomly generated number. If this is not the first communication, for example, you log in to an online shopping website, then you closed the website, then you reopen the website shortly. In that case, you probably do not need to relog in the online shopping website. It's because the web browser retains the cookie session information. So the server can recognize, the online shopping website can recognize who you are. If this is the case, the server replies, server hello, this packet, to the client directly. They do not need to renegotiate the cookie and session number. Then the server passes its certificate to the client to show who the server is as a certificate to validate itself. Then the server sends key exchange to the client. Certificate request, it depends. Usually like the online shopping, the server will ask the client for the username and password to authenticate themselves. But if it's like online banking for security purpose, it might not be asking for just username and password, probably would ask you for a certificate as well. At least in mainland China, most of this online banking, you can apply for a mobile certificate. The certificate is stored in a USB key. So every time you log into your online banking, you need to use this certificate USB key to show the certificate to the server. So let's assume the server requests the client to present a certificate to validate the client self. Then the server hello is done. The client passes its certificate to the server. Client key exchange sent to the server. Certificate verified. Then the client changed cipher specification with the server. Client side finished. The server replied and sent the change certificate specification to the client. They negotiated to each other. If the cipher specification match each other, they are compatible, then it's finished. The communication can be started. If the cipher specification they don't match each other, then the session will be denied. It won't happen. Nothing will happen until the negotiation is successful. So this is at high level how the communication started and negotiate with each other to start the communication. The next slide is Wireshark capture for the DTLS handshake. As it shows here, it's a client hello, and this is client hello again. It has two client hello. Most likely, it's the situation here. This is the first communication between each other. There is no existing cookies and session for this communication. That's why in this Wireshark capture, you can see two client hello at the front. For this detailed practice about the Wireshark capture to understand the DTLS handshake, we will go through these details in the lab session. These capture examples, can be downloaded from a Wireshark website. So for this course, we just skip this one. We will go through these details in the lab session. And you can practice by yourself. You can go through this after the class. This slide is the same. We will leave this to the lab, and you can read this and learn this, practice this by yourself in the lab. We have had certificate with digital signature and secured communication between controllers. It is time for us to establish the secured communication with vEdge. The first element is identity. Identity. There are three types of identity. The first one is vEdge router identity. Second is vEdge cloud router identity. The third one is controller's identity. Let's have a look for the first one, the vEdge router identity. What is vEdge router identity? The physical vEdge router is uniquely identified by the chassis ID and the certificate verified serial number, which is stored in onboard tamper-proof module, the TPM. It is installed during the manufacturing process. We cannot change that. The certificate is signed by AVNet root CA, trusted by control plane elements. Semantic root CA chain of trust is used to validate control plane elements. Alternatively, enterprise root CA chain of trust can be used to validate control plane elements. So basically, you can use semantic root CA to validate the control plane elements as in software, or you can create and build a root CA by yourself in your own environment. But you need to protect this well. Basically, AVNet is the root CA for the certificate at the hardware level for hardware solution. Semantic is a root CA for the software. The second one is vEdge cloud router identity. OTP, one-time password token, is generated by vManage. One per chassis ID in the uploaded vEdge list. This token is used to onboard the vEdge cloud router. We will go through this process in the lab. When deploy the vEdge cloud router in the public cloud, for example, AWS and Azure, the process is a little bit different. The OTP token is supplied to vEdge cloud router in cloud router initiate during the VM deployment. You need to export bootstrap configuration where you can find the device serial number. Then import the device serial number in the public cloud. This is the way to put the vEdge cloud router in the whitelist for this solution to be used. vManage signs certificate for the vEdge cloud router. Post OTP token validation. If it is vManage cluster, vEdge Cloud issues CSR. Certificate is signed individually by each member of vManage cluster. For example, if there are 3 vManage servers in the cluster, each member will sign CSR, and a total of 3 signed certificates will be installed back into the vEdge Cloud. This still provides single router identity, but it's separately validated 3 times. once the certificate is signed by vManage, vManage removes OTP to prevent reuse. By default, the cloud solution uses vPTELA certificate. The hardware solution uses AVNet certificate, as the diagram shows here. If it's a vCloud solution, the cloud solution, it uses vPTELA certificate. And if the hardware solution, like the slide shows this one, the hardware solution, it uses AVNet. Controller's identity is more complicated. By default, it has 3 types: semantic, AVNet, and vPTELA. Three types. Long story in short, when it is vEdge routers to be on board, it uses AVNet as the root CA. If it is vEdge cloud routers, it uses vPTELA root CA. And if it is to authenticate other controllers, it uses semantic root CA. vEdge and controllers, the entire architecture, they operate based on whitelist model. In vManage GUI, administrator adds controllers including vSmart and vBounds in the whitelist. The certificate signing is automatically through semantic. vManage itself is locally recognized. Then controllers list is distributed by vManage to all controllers. By doing that, all controllers, they know each other. The triangle relationship over here, it's the management plane. We have vManage, vBound, and vSmart. Once they are in the whitelist, the information of each other will be distributed by the vManage to other controllers. The information will be synchronized, so they know each other. For the vEdge, at the bottom, administrator needs to upload the digitally signed vEdge list in the vManage GUI. So once again, the import is here by administrator in the web GUI. Both physical and virtual vEdge need to be uploaded in the whitelist. Once the list is uploaded, it is distributed by vManage to all controllers again. This is the way how the whitelist model works, right? So everyone in this architecture needs to be whitelisted, and the whitelist needs to be distributed and synchronized between each of these controllers to know the vEdge as well. This is the high-level security architecture to ensure the device, they are legitimate to connect into the SD-WAN environment. The mutual trust between vEdge, vSmart, vManage, and vBound. There are 2 parts. The first one is vBound to validate the trust for vSmart, vManage, and vEdge. So first part is vBound to validate the other 3. So vBound validates certificate serial numbers against authorized whitelist from vManage and validates organization's name that received certificate OU against locally configured one. The second part is vSmart, vManage, vEdge, 3 components here. These 3 to validate the vBound. So vSmart, vManage, and vEdge to validate the trust for vBound certificate root CA. Same as the first part, it validates the organization name that received certificate OU against the locally configured one. By doing these two parts, the two-way mutual trust is established. Mutual trust between vSmart and vSmart, between vManage and vSmart. There are two parts as well. The first one is vSmart to validate the trust for other vSmart and vManage certificate root CA. Also to validate the certificate serial numbers against authorized whitelist from vManage and organization name that received certificate OU against the locally configured one. The second part is vManage to validate the trust for vSmart certificate root CA. Also to validate the certificate serial numbers against authorized whitelist from vManage and organization name that received certificate OU against the locally configured one. Mutual trust for vEdge to vSmart and vManage. So the vEdge here for vSmart and vManage, it's the same idea. It's the same idea about how they are exchanged and mutual authentication takes place. So two parts. The first one is vSmart and vManage validate, right? Trust for vEdge certificate root CA. Certificate serial number validate this against authorized whitelist from vManage. Organization name, right? Against the local configured one. The second part, vEdge validates trust for vSmart and vManage certificate root CA. Organization unit, organization name against the local configured one. It's the same idea. When we deploy the SD-WAN solution on the over the public internet, the most common concern is a DDoS attack. Cisco SD-WAN solution has taken this into consideration already. Let's have a look how it protects for the SD-WAN solution against DDoS attack. For the vEdge routers, this is the vEdge router. By default, it only allows 3 sources to communicate to this vEdge router. 1, 2, 3. The first one is authenticated source. For example, the vBound, vSmart, vManage, right? It's by default, they are allowed it to communicate it to this vEdge router. The communication is encrypted by DTLS. The second trusted source is implicitly trusted source. For example, other vEdges. The communication is through the SD-WAN IPsec tunnel. The third one is explicitly denied source. Explicitly defined source. Like the cloud security, it's in the public cloud. The communication would go through the IPsec and GRE tunnel. These 3 are permitted by default. For others, for all other unknown sources, it's denied. It's a red, it's a deny. There is an exception. If the traffic is return packets matching flow entry, DHCP, DNS, ICMP. For example, if the traffic is a return traffic, it would be allowed coming out from this vEdge router. The DDoS protection for controllers is similar idea. By default, only authenticated sources are allowed. It only allows vBound, vSmart, vManage, and vEdge, everything in the whitelist. The communication is encrypted by DTLS. For any other unknown sources, it's a deny. Right? It's not allowed. Exception here is DHCP, DNS, ICMP, netconfig. The next one, let's talk about the SD-WAN controller deployment. There are 3 models available on the market right now. The first one is Cisco Cloud Ops. This is a controller cluster. This is the controller cluster provisioned and managed by Cisco. As the customer, the end user, you can consume this solution. As a service, you just pay the subscription to the Cisco and you get this service, you can consume that. The second model is MSP Ops Team. MSP means Managed Service Provider. For example, like Telecom, Vodafone. They can host this solution, the management cluster, by themselves, whether it's in the public cloud or in their private cloud. And they provide the maintenance services, and you can consume this, you can subscribe that, and consume this as a service. These 2 solutions, basically they are the same. The only difference is at the back end. Who manages that, right? If Cisco manages that, it's Cisco Cloud Ops. If it's managed by the service provider, it's MSP Ops Team. Mostly commonly used probably is this one, the enterprise IT model. It's the customer themselves to deploy the management cluster and manage this by themselves. For the controllers, there are 2 types. The first one is single tenant. For example, if the customer deploy this and manage this by themselves, it's probably its dedicated cluster. So this would be a single tenant model, because you have only one customer and you are the only user. This belongs to you. You have the vManage, vBound, and vSmart. The other model, if it's provisioned and managed by Cisco or by the MSP, managed service provider, the architect can be, it supports multi-tenant as well. You can have vManage, vBound, and you can divide them, you can share this to provision this to multiple tenant on the same device. In this diagram, we can have tenant 1, 2, 3 of them. So the vManage and vBound, they can be shared, but vSmart cannot. vSmart is used to separate the traffic. So each tenant, they need to have at least one smart. In this case, this is vSmart for client A, tenant A, this vSmart for tenant 2, and this is vSmart for tenant 3. So once again, the vManage and vBound, they can be shared by multi-tenant, but vSmart cannot. At least one vSmart per tenant. For the controller's deployment methodology, 2 types. It's easy. One is on-premise or SP hosted. But whoever hosts that, it's on-premise, on the physical server. Bottom is the physical server, and you virtualize this by VMware or KVM. Then on top of the VMware or KVM, you provision the vBound. vManage, vSmart. And you can have multiple vSmart if you have multiple tenants. The other type is cloud hosted in the public cloud, for example, AWS or Azure. And vBound, vManage, vSmart, over here, they are virtual machine or container. You can run them as container or virtual machine. So 2 types. One is on-premise, the other is cloud hosted. Really depends on your business requirement. For the vManage deployment, you can deploy it in cloud or on-premise. Once the vManage starts up, there are 2 interfaces by default. One is called VPN 0, the other is called VPN 512. What are they used for? As the diagram shows here, VPN 0 is service interface. VPN 512 is management interface. It's basically the outbound management interface. The VPN name here is not VPN. It actually means VRF. And both of them has zone-based security. When you bring them up, you need to have the minimum configuration to bring them up. For example, you need to configure the connectivity system IP. You need to give it an IP address for the management access. Site ID, organization name, vBound IP. vBound deployment. It's the same as vManage. The only difference here is the vBound IP. Because this is vBound, it is itself. It would be local. So be aware of this one. This is the only difference between the vBound deployment and the vManage deployment. The rest, they are the same. vSmart deployment, it's the same, right? You have 2 interfaces, one for service control, the other is for management interface. They have zone-based security, and you need minimum configuration for connectivity, system IP, site ID, organization name, and vBound IP. This is controller's basic configuration comparison. We have vManage, vBound, and vSmart. The essential difference is here. It's local, right? vBound is local because it's a vBound. This is basically the only difference between the 3 controllers configuration. Just the highlighted local here. And the rest of this, you need to configure the IP, you need to open the services, and add the default route. That's it. That's the basic configuration for the controllers. For the interface usage, VPN 0 and VPN 512, VPN 0, as we said, this is used to establish DTLS connection. This is for the service control. VPN 512 is used as an out-of-bound management for controllers. And the control channel is always sourced from VPN 0, encrypted by DTLS, like the diagram shows here. The controller's connection. In most of the cases, it would like this one. All of this communication and data coming out, in and out through VPN 0. through the cloud network. All coming out and communicate based on VPN 0. Also with the vEdge as well. This is the most common case. To add controllers to the vManage, the vManage will use its VPN 0 interface to log into vBound and vSmart to include them in the controller's whitelist. Like the diagram shows here, vManage will always use VPN 0. But for the vBound, vSmart, there are two options. The first one is use VPN 512 interface. The vManage UI requests to use the management IP of controllers with user credentials, as by default, the management interfaces are enabled for netconf and SSH. So there should be routing between the VPN 0 subnet and the VPN 512 subnets for controllers. So this option, we need to enable the routing between the VPN 0 interface with this VPN 512 in order for the vManage interface VPN 0 to communicate to each other. This is the default solution, default design for the public cloud in AWS and Azure. The second option shows here. It's much easier. Everything is communicated through VPN 0, right? So if we deploy this in your own environment, option 2 is recommended. It's much easier. But if we are going to deploy this in the public cloud, then you would have to use option 1. For the site ID, vSmart and vManage point to vBound IP address, like the diagram. These two, they would always point to vBound, the netted public IP address. Then vBound, it's a net over here. Then vBound learns interface private IP, private and netted public IP address of vSmart and vManage. The relationship here. vBound will try to learn this relationship. So it knows both public IP addresses and both private IP addresses and public IP addresses. So the most common deployment is to use same site ID as this diagram here. By doing that, if it's with the same site ID, the vManage and the vSmart, they will communicate to each other through the private IP address. It's much easier. It's just a LAN traffic. But if with different site ID, the story is different. The first part is still the same. vSmart and vManage, they point to the vBound, the netted public IP address. And vBound learns the relationship, private public IP address relationship from vSmart and vManage. These steps, they are the same. The difference is the next. If the site ID is different, then the vManage and vSmart, they will talk to each other through the netted public IP address. It's not by the private IP address anymore. This is the only difference. Just be aware of this. If we are doing the solution, take this into consideration, whether you would like them to communicate through a private IP address or public IP address. The next is SD-WAN deployment with firewall. We will leave this topic to the next class. So thanks for watching, and see you in the next class.